So as Cameron said, this first lecture is going to be a short lecture on talking about, well, should I use diffusion wave or full momentum, or what we call the shallow water equations? And the main objectives of this lecture are to give you an overview of the diffusion wave and full shallow water equations themselves, and then learn about the positive and negative attributes of the diffusion wave equations, as well as the positive and negative attributes of the full shallow water equations. And then I'm going to show some examples so you can really see the impacts of one equation versus the other. So let's talk about the equations. So for the full shallow water equations, we have basically mass conservation continuity equation, which is basically it's just, the inflow to a cell minus the outflow to a cell is equal to the change in volume of water in the cell. Okay, so that's just continuity. But then the real equation that controls water movement is the momentum equation. And for the full shallow water equations, we have terms for gravity, friction, hydrostatic pressure differential, acceleration terms, both local and convective. And local is change in acceleration at a point with respect to time, and convective is change in acceleration with respect to distance. But then there's options for eddy viscosity, turbulence modeling, Coriolis effects if you're in the northern southern hemisphere, and then wind forces. Well, diffusion wave is the exact same mass conservation equation, but the momentum equation in diffusion wave is very limited. There's only 3 terms: gravity, friction, and hydrostatic pressure. So the main thing that's missing is those acceleration terms, that local and convective acceleration. Those are important terms for certain types of problems. And additionally, you can't turn on turbulence, Coriolis, or wind forces if you're using diffusion wave. You have to go to the full shallow water equations. So here's the equations in 2D. And I'm not going to go through all the terms of the equations, but the point here is that the top one is the 2-dimensional momentum equation in 2 directions. U is a velocity in the x direction, v is velocity and laterally. And then those are all the terms there. But on the bottom is the same 2 equations, but the only thing that's left are the 3 terms. There's like G for gravity, partial of h with respect to distance is the change in the pressure differential force, and the CF is the coefficient due to friction times the velocity. And those are the 3 forces. So you can see there's way fewer terms. But again, the main terms missing are the acceleration terms. Okay. Let's talk though about what are the positive attributes of the diffusion wave equations. Well, first of all, when you use diffusion wave, you're using and hoping to work on problems that are predominantly gravity and friction driven. Okay, so it's better off for steep to moderate sloping streams. And I put a kind of a rule of thumb there of a slope greater than 2 feet per mile, because I've done a lot of studies on different equations and how they react to slope just in general. And once you get down to about 2 feet per mile and less, gravity is lesser and lesser of a force, because as you go towards a slope of 0, gravity force is 0, right? And the velocities are slower, and if the velocity is slower, that means friction losses are less too because of the slower moving velocities. And when you get down to those flat slopes, then wave propagation starts to become important. And wave propagation is really best modeled, including not just gravity and friction, but those acceleration terms. Okay. The other thing that is good about the diffusion wave method is it can handle hydrographs that rise and fall slowly, because if they're rising and falling slowly, then the change in velocity with respect to time and distance isn't changing very much over time. And so those forces are small. And it's not until you get to rapidly moving hydrographs that those forces become large. So if you have moderately rising and falling hydrographs that rise and fall slowly, diffusion wave can handle that because the acceleration terms aren't that great compared to gravity and friction. The other thing is the diffusion wave equations are very stable. They can handle larger time steps than the full shallow water equations. And in the documentation, we even say you can pick a diffusion wave time step by setting the Courant condition to 2 for a base kind of time step. But it can even handle Courant numbers all the way up to 5, okay, or larger. And so which means it can handle higher time steps. So just some basic comments then are diffusion wave is good for computing like rough global estimates such as the flood extents. If you are doing dam breaks, you can still start out with diffusion wave and get kind of a roughly built dam break model, but you should always try and test, well, what if I were using the full equations, would I get the same answers? Okay, and if it's a dam break and it's really rapidly rising and falling, you probably won't get the same answers, which means you should be using the full equations. It's also good for assessing interior areas for where levees breach, okay? And a lot of times I use it as a starting method until I get my model up and running and stable. And then once I get my model up and running stable, then I'll turn on the full equations in a second plan and run it. and see what the differences are, and then make the decision of what I need. So the negative attributes of the diffusion wave equations are it's not good for fast rising and falling flood waves, okay, like we talked about, so dam breaks and flash floods. It can be problematic there. It's also not good when you have really sharp contractions and expansions, and we're going to look at this in detail with an example. And the reason is that in a contraction, you have a dramatic change in velocity with respect to distance, and same thing in an expansion. Well, that term is not included in the diffusion wave equation, so it's completely missing the forces associated with when water contracts and expands, okay? And it also can't handle and compute recirculation zones in the expansion. You won't get any eddies forming when you use the diffusion wave equation. You have to have the full shallow water equations for that. Another very problematic area for diffusion wave is tidal boundary conditions, because a tide rising pushes in and it's a wave, and that wave propagates upstream, and there's definitely the propagation of that wave requires the acceleration terms to handle and model correctly. It's not good for sharp bends because it can't predict super elevation around a bend. And it's really not as good for predicting detailed velocity distributions both in a channel or around any objects because it doesn't have those acceleration terms and the intricacies of velocities in the channel or around, especially around object, that acceleration and deceleration becomes really important in the equations to getting the right velocity distribution. And then finally, it won't work at all for mixed flow regimes where you have subcritical to supercritical flow and then hydraulic jumps. It can't even compute a hydraulic jump without those acceleration terms. So the full momentum should be used in the following situations. Definitely for highly dynamic flood waves like dam breaks, flash floods, where you have abrupt contractions and expansions with high velocities as well as the flow approaching structures on an angle, okay, you need those full shallow water equations. In really flat systems where gravity is no longer the dominant force and friction, that's also where you need the full shallow water equations to get the propagation of water moving around correctly. So slopes less than 2 feet per mile. Where you want detailed velocities and water surface elevations for both in the channel and around structures. If you have mixed flow regime, you need the full shallow water equations, especially if you have any hydraulic jumps. Tidal boundary conditions, you absolutely need the full equations, which you're going to see in an example here in a minute. Super elevation, and then just general wave propagation. So let's say you have like you're opening and closing structures really quickly, whether that's in a canal or even a natural river. If you open a structure quickly, you have a rapidly rising hydrograph, which means the change in flow, water surface, and velocity are going to change rapidly with respect to time and distance. And you have to have those acceleration terms to model that accurately. And then if you want to use turbulence, wind, and Coriolis, you absolutely have to use shallow water equations. We do not even have those as options for the diffusion wave equations. Okay, so this is an important thing right here. So how do you just test any model to know if I should use diffusion wave or shallow water equations? Well, you create two plans, and the only thing you change is which equations you're going to use. So you create one plan where you turned on diffusion wave, you create another plan with full shallow water, you run them both with everything else exactly the same, okay? And then you compare the answers. You compare water surfaces, velocities, flow rates at all kinds of locations within the study. And if you're not finding really any significant difference, then that right away is going to tell you that for that problem and that event, the diffusion wave is working just as good as shallow water. And since you can use larger time steps and it runs faster, you might as well do that. But if you're going to find locations where you have differences in water surface, flow rates, velocities that are significant, then that's trying to tell you, hey, you really should be using the full shallow water equations, because the differences are based on things that have been taken out of the diffusion wave equations and its inadequacies, okay? So you need to think of it that way. Okay, so I want to talk about three things through examples so you can really get this driven home. So we're going to look at a sharp contraction, we're going to look at a dam break model run, and we're going to look at a tidal boundary condition, and we're going to compare these two equation sets. So first of all, here we have our friend Bald Eagle Creek. And when we have that levee system at Lock Haven really necks down the channel. So we have all this flow in the overbank that contracts all the way down, has to go through this small opening through the channel. So upstream of that, there's a sharp contraction zone right here, okay? And here, what I did is I put in a profile line in RAS Mapper down the center of the channel. And here I'm plotting the profile, and the dark blue is the diffusion wave equation, and the light blue is the full St. Venant equations. And what you can see here is there's about a 4-foot difference in water surface upstream of this contraction just by running the different equation set. And even through the contraction and then through the expansion, the shallow water equations are higher because the velocities are slower due to the forces of the contraction and expansion. So here's a location that I could get a 4-foot difference just because I used diffusion wave. I'd be 4 feet too low, okay? Now remember, there's other things that are gonna affect the water surface, like the terrain, the N values, etc. So I could be using diffusion wave and cranking up the N value, but is that really the right thing? I'm not really seeing the true effects of this contraction in the right zones with diffusion wave, okay? So that's important. Here's just a plot of a hydrograph at one location. So at first, at low flow, when all the water was in the channel, they were given the same answer because there really was no contraction, right? But once flow got out into the overbank, then there was more and more contraction force. And at that peak flow, there's 4 feet of difference between the full equations and the diffusion wave equations. Now here's an inundation map, and I'm going to animate this. So I'm plotting on top the diffusion wave equations in green and red, but on the bottom is the shallow water equations, and they're just in blue. But the point here is that it's the same exact event, same model. The only thing different is the two equations. And let's see what happens in time. So at first, the extent is the same, but now the shallow water equations, because they were higher, they overtopped the levee sooner. And so I got water out into Lock Haven way sooner. Now here comes the diffusion wave along now, okay? So there was, because the shallow water equation was higher, it breached the levee sooner, okay, or overtopped the levee sooner. Now the final plot, the extents of the floods looks very similar. So if you're only looking at the extents of the flood, you may not really understand fully the differences that occurred between using the shallow water equations and the diffusion wave, because maybe the water's confined to the certain area of the valley and they're going to show. But in this case, even though the water's confined, the water surface elevations are 4 feet different in places, and the timing of when water got in and over the levee is extremely different. Okay, here's a dam break situation, and I showed this the first day, and so this, I'm not going to go through this animation too much, but this is the Sacramento Valley and the Oroville Dam. So here's Oroville up here. We got flow coming down due to the breach. And so here for a dam break problem, this is just showing the animation from the full equations. But what I did is I ran both this exact same event with diffusion wave and shallow water equations, okay? And I'm going to go ahead and kick out of this animation. And so what I did then is I computed in RAS Mapper, I computed a new layer, which you can do in RAS Mapper, and I said, I want to create a layer that's the difference. And so I took the shallow water equations minus the diffusion wave. So a positive number means the shallow water equations had a higher answer, and a negative number means the diffusion wave equations had a higher water surface. So here's my color chart down here. So values of yellow and dark green are plus or minus half a foot. So they're close to the same water surface. As I get to orange and red and purple, those mean the shallow water equations were higher. As I go down to blue and gray, that means the diffusion wave equations were higher. So here at this time, at this instant in time before the breach occurred on Oroville, there were some differences, but they were smaller. So we got a lot of yellow, okay? There's a little purple here, which means the shallow water equations was higher. But let's go forward some time. Here we're 20 minutes and we're into the breach now. And right up by the dam, I clicked on the water surface and the difference was 34 feet, meaning that the shallow water equations right by the dam in that canyon were producing water surfaces higher than the diffusion wave by 34 feet. That's huge, right? But very quickly downstream of that, for this instant in time, the colors gray and blue, which means the diffusion wave equations were higher. So what that's telling me is because the shallow water equations were higher here, the velocities were slower, but the diffusion wave equations were producing a lower water surface, so it had the flood wave out in front. So what all this means is that the diffusion wave flood wave is already down here, and the shallow water equation flood wave hadn't reached that spot yet, which is why the diffusion wave was giving a higher answer than the shallow water equation. So let's go step forward some more. So here we're seeing a kind of a similar trend. Up by the dam and closer to the dam, the shallow water equation is much higher in this purple, but then it transitions to about the same, and then the diffusion wave is higher because it's sending the water out faster. So it's actually reaching these areas of this overbank sooner, and there's probably not even any water from the shallow water equations yet, which is why the diffusion wave is showing a higher answer. It's in that gray zone. Okay, let's move forward some more time. So similar trend. Up here, shallow water equations are higher. Here they're about the same. Diffusion wave is higher on the leading edge because it's out there faster. Now we're going to zoom out. We're going to see some similar things. Okay, here is late in the simulation. So very late in the simulation, the water surfaces are similar up in here now, but diffusion wave is higher down here because it reached here sooner again. Similar things. And then finally, this is just the maximum extent. So if I had only compared the maximum of extent, and here I got diffusion wave plotted in green and red and shallow water in blue, I don't see a lot of difference in the maximum extent. But what actually happened was very different from a travel time perspective and water surface elevation perspective in a lot of places, even though the extent was about the same. So you can't only look at the extent as an indicator or am I getting the same answers? You got to look at water surfaces, timing of water surfaces, velocities, etc. Okay, let's talk about a tidal boundary condition now. So here's the Lower Columbia, and just for this experiment, I created a 2D model of the Lower Columbia. I originally had a 1D model of this, but I created a 2D model and I ran it both in diffusion wave and full St. Bernard equations. So let's look at an animation first of all. So here's my tide coming in and out. And if you know anything about the Lower Columbia, the tide is high, the tide cycle is high. And it actually will affect the water surface at low flow all the way up at Portland, which is over 100 miles upstream because of the tide cycle. So what I did is I put a profile line right down the center. So I put a profile line right down the center of all this, right down the center of this channel, okay? And right down all the way out to the ocean to the tide boundary. So like that profile line is this entire distance, okay? And so here's the downstream end on the right. And so that they're using the exact same stage hydrograph for tide, but this is at time 0. And you can see there's a difference as you go upstream. The full shallow water equations in this case are in dark blue, and the diffusion wave is in light blue. Now let's animate this. So you're going to see some interesting things when we animate it. So notice the boundary condition is the same on the right, but watch the tide upstream. How high does diffusion wave get compared to the full equations? The full equations gets over 10 feet up here. The shallow water, the full equations get over 10 feet. The diffusion wave only gets a little bit over 8 feet. And notice the difference in how the waves propagate throughout this thing. So in this case, because those acceleration times are not in the diffusion wave, it can't account for that velocity pushing the water upstream and causing a slowing down of the velocity upstream and a higher water surface. Okay, it just can't do it. Now here's a plot of water surface versus time at the upstream end. And again, dark blue is the full equations and red is the diffusion wave. So you can see at the upstream end, the water surfaces are much higher with the shallow water equations. Okay, just in general, because the tide has a much greater effect due to the inclusion of those acceleration terms. Okay.